Hello, everyone. My name is Zhengpeng Lin. I am a PhD student from Penn State. My research focuses on exploitation and defense on complex software. Today, I'm going to talk about exploitation in Linux kernel, specifically how we turn unexploitable bugs into exploitable ones, and how we utilize the same method to find the exploit primitive automatically. We will demonstrate this on the exploitation of a real-world kernel bug in CentOS kernel. This work is done with the help of my collaborator Yueqi Chen, my advisor Xinyu Xing, who are from Penn State as well, and my mentor Kan Li from Baidu Research USA. I'm going to start with a bug example that shows different memory corruption in two kernel sites. And then I will introduce the definition of multiple error behavior of bugs. After this, I will talk about a new approach to turning unexploitable trash bugs into exploitable ones. With this approach, I will show how an ignored trash bug in CentOS kernel was successfully turned into an exploitable one, which in reality has powerful memory corruption abilities like leaking kernel data and hijacking kernel control flow. And finally, I will talk about the implication of multiple error behavior to kernel security. Before moving to the example of bug, I would like to discuss what it means in terms of unexploitable in this talk. In general, an unexploitable bug is a bug that is likely to exploit. To exploit a bug, we usually start from an error. The error allows you to create another error. Eventually, you achieve your goal from an error you created. For example, you want to hijack kernel execution. You start from a memory overflow error. Then you utilize the overflow to overwrite a function pointer, which results in another error, and this provides you the kernel execution hijacking. When we say unexploitable, we basically mean that the error we found is not able to propagate to other errors that will lead to our exploitation goal. The difficulty of propagating errors is from the block of mitigation and the limitation of original errors. For example, mapping memory at zero address is not allowed in Linux kernel, which blocks the propagation of a non-pointer dereference error. Accessing memory address not in page table is not allowed as well. So errors like general protection fault and non-pointer dereference cannot propagate. Sometimes the error doesn't have memory corruption ability, like warning bug on error. These are kernel debugging features. They will generate a warning message without corrupting kernel state, so it cannot propagate as well. Compared to other errors, they will demonstrate severe memory corrupting ability. Less likely to exploit errors get less attention from the community. Here is the statistic from historical kernel CVEs. The UF, out-of-bound, double-free errors make up the larger portion of CVEs. The second largest one is errors with limited memory corruption ability, like general protection fault and non-pointer dereference, which account for 31% of CVEs. Errors without memory corruption only make up 1% CVEs. Other than smaller portion, the CVSS score for this type of bug is lower as well. The average CVSS score for UF, out-of-bound, double-free errors is 6.17, while the average score for general protection fault, non-pointer dereference, is 5.48, and the death for warning is 3.75. So they get less attention. When we see an error like warning or non-pointer dereference, we may think they are unexploitable. In other words, they are trash bugs because their memory corruption ability is limited. But most exploitation requires memory corruption. However, this may not always be true. This is a real kernel bug being fixed in upstream silently. Here are some code snippets of the bug. There are 3 functions contributing to the error. Let's go through it one by one. The first one is the tongue attach function. The tongue flag here is controlled by users. In this function, if the NAPI flag is enabled, which means the if condition is satisfied, it will initialize a timer and link current NAPI to the list of the device. Otherwise, there will be no timer and current NAPI will not be linked into the device. The second function we need to look at is the tongue detach function. These two are a pair, attach and detach. Here, if the NAPI flag is enabled, it will cancel the timer from the NAPI object and remove the NAPI from the list. Otherwise, the kernel thinks the NAPI functionality is not enabled and it will not cancel the timer and will not delete the linked list. But eventually, it will destroy the file, which will free the memory of the NAPI object. The last one is the function to free the device. When it's called, it will go through the NAPI list and see which one is still in the list and destroy them one by one. Now let's look at how the bug will happen. Since the tongue flag is controlled by users, users can specify inconsistent flags between the tongue attach and the tongue detach function. Specifically, if user disable the NAPI flag in tongue attach function, the timer in the NAPI object will not be initialized, and the NAPI will not be in the list. And then the user enable the NAPI flag in the tongue detach. It will cancel the timer. And inside the timer cancel function, it will dereference a pointer in the timer object. But since the timer is not initialized, so there will be no valid pointer in the timer object. So the kernel will dereference a non-pointer and generate a pointer dereference error. A question for this is whether this error is exploitable. The execution always leads to access of the timer object, but the timer object is not initialized, which is full of 0, so it will always dereference a non-pointer. However, mapping memory at 0 address is not allowed in Linux kernel, so this error is less likely to exploit. The bug could actually have a totally different error behavior if we trigger it differently. This time, we enable the NAPI flag in the tongue attach function. And we will have a timer initialized, and the current NAPI will be linked in the list. Next, we disable the NAPI flag in the tongue detach function. So the NAPI will be still in the list, but it will destroy it by the file. Next, we free the device, and the kernel will go over the NAPI list and access to the NAPI object, which was freed in the tongue detach function, and this will result in a UF error. The error becomes different. How about the exploitability? Exploiting this UF is straightforward. The vulnerable object is allocated in general cache, which means attackers can allocate another type of object in the same cache. Looking at the definition of the object, it contains an escape buff object. So when freeing the NAPI struct object, you will free the escape buff inside. An attacker can get a control flow hijacking ability when freeing SK buff. Because the free of SK buff will dereference a function pointer inside the SK buff. By spraying memory, attacker can temper the SK buff pointer to a fake object, where the function pointer can be controlled. After this, attacker can obtain a control flow hijacking ability. In this case, we successfully turned the unexploitable crash to an exploitable UAF for the same bug. The UAF doesn't require a complicated exploitation method. You spray the memory and you will be able to hijack the kernel execution flow. Why this is possible to kernel bugs? Because kernel bugs are complicated. The same bug could cause different crash behaviors that we call them multiple error behaviors of bugs. When the bug is triggered differently, it shows different error behaviors. In this case, it's different inconsistency of time flag between the time attached function and the time detached function. Error behaviors demonstrate bug effects, which indeed is the memory corruption ability. When we expose multiple error behaviors of bugs, we will be able to figure out the memory corruption ability of the bug. For example, we will be able to know the bug could cause a UF other than a non-pointer dereference error. Different bug effects represent different exploit potential. When we see a kernel always crash with a non-pointer dereference error, the bug might be less likely to exploit. However, when we find a new input that will cause kernel to generate a UF error, we might be able to utilize the UF to do exploitation. So with different bug effects exposed, we will be able to find bug effects that is most likely to exploit to have a better estimation of exploitability. And we probably will turn unexploitable bugs to exploitable ones. But how to do this? First of all, to find the multiple error behaviors of bugs, coverage-based fuzzing is not suitable because we need to trigger the same bug differently to expose their multiple error behaviors, which need to test on the same piece of code over and over again. However, coverage-based fuzzer by design will try to test on new code as much as possible. Intuitively, this is contrary to our goal. So we propose an object-driven kernel fuzzing. The insight of our approach is to use kernel objects to bound the fuzzing scope. We use the reachability of the kernel objects as an additional fuzzing feedback. This feedback allows us to differentiate inputs when the bug is triggered differently. We implement our approach as a customized fuzzer based on syscaller. Specifically, our first step is to find the kernel objects. We take the crash report as input. We start from the code where the crash happens. Then we backward analyze the diffuse chain of the data. Along the way, we collect the type information of the data flow. Here is the example of how we identified the object for fuzzing. In this case, it's a non-pointer dereference in timer active function. We backward analyze and first find the timer structure. Then we follow the data flow and we find the NAPI struct and time file structure in the time detached function. With the objects on hand, we then use a customized compiler to instrument the basic block, which are involved with the operation of these objects. The instrumented code will send object feedback to the fuzzer when it's executed. So in addition to code coverage, we also have object coverage as a feedback to fuzzer. We also have a new seed selection and a new input mutation approach based on the feedback of object. Our tool and other details will be released soon. Kernel objects, kernel bugs have multiple error behaviors, which represent different exploit potential. As such, a bug with similarly low security error could have other severe errors that result in exploitation. So what does this mean? To kernel vendors, don't rely on single error behavior to estimate the exploitability of bug. When you see a bug shows warning error, the bug might be able to cause a UF somewhere else. Relying on single error behavior of bug could underestimate the consequence of them. So please fix all the bugs if there has a patch from upstream. You never know whether a trivial fix is a critical security fix or not. And to offensive technique researchers, a similarly trash bug could result in exploitation. You see a warning report for a bug, you might be able to see a UF error if you expose the other error behaviors of that bug. Other than that, exposing error behavior also help you find better primitives for exploitation. For example, you already find a UF, exposing other error behaviors will tell you other primitive this UF has. Lastly, there might be a lot of unfixed, exploitable bugs in vendor's kernel. These unfixed bugs may look like non-security bugs firstly, but if you expose their other bug effects, you might be able to observe severe memory corruption ability. We have a perfect example for this. This CVE was fixed in upstream back in March 2020. It was first discovered by SysCaller with a warning error. But in reality, it could result in severe UF error if the bug is triggered differently. We investigated whether it's fixed in vendor's kernel. It turns out by August 2021, it's a 0-day in CentOS 7's kernel and other CentOS-based distros like Tencent OS and AliOS. All right, let's look at the bug. So on the right side, it's the error message generated by KSAN. It detailedly logs the allocation and the free of the vulnerable object for the UF. The vulnerable object is allocated by KZalloc in ROTeful change function, and it's freed by work queue in ROTeful delete filter. And it turns out the free work was queued by ROTeful change function as well. So the vulnerable object is allocated and freed by the same function. And the UF error is triggered after the free object is accessed in another function. So what does ROTeful change do? It basically does two things. The first thing is to allocate a ROTeful filter object. When users request a new filter to kernel, it allocates the object and initializes it properly. The second thing it does is to update the ROTeful filter object. When users request to modify the ROTeful filter, it first allocates a new one and then copy the content of the old one to the new one. And finally, it will remove the new one and free it. The ROTeful object is managed in the linked list. So when updating, the correct operation to delete the old ROTeful object is to remove it from the linked list, then free it. It's wrong if we remove the new one from the linked list and free the old one. And this is exactly how this bug happened and how the bug is fixed. Here is the patch to fix the bug. The code in red is the root cause of the bug, and then the code in green is why it's fixed. The bug only removes the new allocated object from the list, and then the old one gets freed in the following. So we will have a freed object in the linked list. This is the bug report that the SysCaller first identified this bug. It shows a warning error that happens at calling RCU. It requires collision to trigger, So the first glance of this bug report will give you the sense that the trigger of this bug is very unstable because a lot of unreproducible bugs are related with RCU operations. However, based on this bug report, using our tool, we are able to find its other error behaviors and discover other exploit primitives automatically. This is the UF error triggered when the freed object is accessed in the rootful get function. And this is another UF error triggered when the freed object is accessed in the rootful destroy function. And this is another UF error found by our tool automatically in the rootful dump function. Different UF errors in different functions represents different exploit primitives when doing exploitation. These automatically discovered primitives are very useful in the exploitation of this bug. Let me show you how we use them to exploit this bug. So, for example, we could utilize the automatically discovered primitive to bypass KSLR. Looking at the UF error found in rootful dump function, the function has several calls to NLA put function, which will send kernel data to user space. And this means that some data fields in the vulnerable object will be leaked to user space through the rootful dump function. To bypass KSLR, we can spray kernel pointers in the leaked field, and then trigger the rootful dump function to read kernel pointers to user space. To hijack control flow in the exploitation, we could also utilize the automatically discovered UF error in the rootful destroy function. The function will queue a kernel RCU work in which a function to handle the work will be stored in the object. Specifically, looking at the definition of rootful filter structure, there is a nested data structure called RCU work, which stores the information of the RCU work. And inside the RCU work structure, there is a structure called work structure, which contains a function pointer to handle the work. So indeed, there is a function pointer inside the vulnerable object. Attackers could spray kernel memory to overwrite the function pointer after queuing the RCU work. And eventually, attacker will obtain a control flow hijacking primitive from this UF error happened in rootful destroy function. In summary, bugs have multiple error behaviors when they are triggered differently. For example, a bug may generate a non-pointer dereference error and may generate a UF error. With multiple error behaviors of bug exposed, we will be able to find the worst bug effects to determine the exploitability of the bug. In addition, we can also utilize it to help discover exploit primitives and find the inputs for it automatically. In this example, we are able to automatically find the exploit primitives that help bypass KSLR and obtain control flow hijacking ability. In addition to utilizing automatically discovered primitive to exploit this bug, I would like to talk about a generic exploitation method for exploiting UAF in Linux kernel. The exploitation only requires free ability from the UAF. Specifically, the UAF should be able to free the vulnerable object again after spraying another object to occupy the memory slot. Also, I will utilize the universal spray objects to achieve leaking and racking ability. So, to apply this technique in exploiting this bug, we first free the vulnerable object. After freeing, the memory is freed, but there has a dangling pointer referencing it. Then we spray the universal spray object to occupy the memory slot. Here we use the message structure. It's a flexible structure, so it can be allocated in any general caches, depending on user control. Then we free the spray object through the vulnerability. This is the place where we utilize the ability of the vulnerability. After freeing, the message object becomes freed. After this, we spray a victim object which contains pointers. It could be function pointers or heap pointers. Then we call the store message function, which will copy the content of the object message to user space. And this will leak the content of the victim object to user space. So we will be able to leak kernel data. And we could also temper the function pointer inside through the message object to get control flow hijacking ability. The whole process is very standard, and it has the potential to be developed as an automatic exploit generation approach for exploiting UEF in kernel. I have implemented the exploitation method in exploiting this UEF, this CVE, and I believe a lot of code can be reused in exploiting other UEFs in kernel. There is one more thing about exploitation. Sometimes we have the control flow hijacking ability, but we cannot control the arguments of the control flow. For example, the argument is always a heap address. And we cannot hijack control flow to run command function because the argument is not pointing to a string buffer that we can control. And we cannot call to native read CR4 function because the first argument is a heap address, which cannot help us disable SMAP and SMEP. In this situation, we can try some function gadgets in kernel. For example, the install execute cred function before kernel 5.8 or the commit NSSet after kernel 5.7. These two functions contain perfect gadgets that will change the credential of current process. Specifically, looking at the install execute cred function, as long as we can set the cred field of the argument to init cred, which is a global variable, we are able to change the credential of our current process to root. The code is available in my GitHub repo. You are welcome to take a look at it. Finally, I would like to summarize several takeaways here. First, a kernel bug could have multiple error behaviors. So when you see a trash bug, it could result in severe memory corruption if other error behaviors exposed. So for vendors, please adopt fixes from upstream, even if it fixes trash bugs. Second, we could utilize the tool to find multiple error behaviors of bug and find the exploit primitives automatically. As shown in the example, we are able to find primitives of bypassing KSLR and hijacking control flow automatically. Lastly, there might be other unfixed exploitable bugs in vendors' kernel because most vendors only fix CVE bugs, but a lot of bugs don't have CVEs and their exploitability are unknown to them. These bugs could be very severe, but look like trash bugs, so they get ignored. Checking whether vendors adopt fixes from upstream could be a great way to hunt for 0 days. That's all of my talk. This is Zhengpeng Lin from Penn State. My research focuses on exploitation and defense. You can find my other information from my personal website. I'm looking for internship for next summer, so if you know there is any opportunity, feel free to send me a message. Here is my Twitter, and you can find my other contact information from my personal website as well. It's a great honor being here to share my work. Now I'm happy to take questions.